And of course, so I will take this result you know about the cross product by Z as something I will try to prove 3 times. Okay, so what it says, so we have a sister algebra A, and you have a group action of Z, so just not on items, not on A. And okay, you can build the cross product. And the question is, can we compute the K-theory? And the answer is that this is now 35 years ago, something like that, in the 80s, beginning of the 80s. There is a perfect answer for this question. Okay, the proofs. That's, I mean, people that look at the results say, okay, this is just the first step in a bunch of general results for the K-theory of groups, or with decoration with this algebra. And we know very general methods to do that. Okay, built by Baum-Cohn conjecture, Kasparov, and it's called the Dirac method. So it uses geometry a lot. And in particular, you have to find some space nice for this Z action. And you build things out of it. So I will show you a very short proof of how to compute this using idea in this direction. It's not new, it's not Blackadder proof, so there's just another one. What you do is you consider this algebra, A, and you look at the cross product by R times Z. Okay, the R is just acting by translation on C0 of R, and the Z it's a diagonal action, because we know it acts on A, and we're also translating by 1 in C0 of R. Okay? And then, can we understand? I mean, this, of course, these two action commutes, that's why it's the cross product. And then you can try to figure out what this is. Okay, so maybe the first thing is you just do first, no, maybe the difficult one that I will state already is what is this? Because it commutes, you can do this cross product transaction in about 2 steps. When you look at this, you can prove that it is Morita equivalent to this algebra, which is function, let's say from 0, 1 onto A, with the property that f of 1 is alpha of f of 0. Actually, if you have no A, this is the torus, just okay, and C0 A cross product by Z is isomorphic to Morita equivalent to the torus. Is a well-known thing on groupoid equivalence, if you want, of R cross Z with T. Okay? So now you have to prove that this Morita equivalence actually is compatible with the action of R, which is okay because it's just on the space. So now what you have is that this algebra A is actually something like this algebra cross product by R. Okay. On the other one, and this is the easy part, if you just do the C0 of R cross product first, so it's such A cross product R, and then this, because R is just acting here, and this is a dual action, you get the compact. This is just K, the compact operator from the space times of A, and now when you add this Z action, you add that A is compact, so H times A times Z. Of course, the Z is acting on the K, on the compact operators. But we know that automorphism of compacts are given by, are inner, actually, given by unitaries. So you can untwist this action on the compact. And this actually turns out to be isomorphic to the compact tensor, the cross product. But now you're done, because now you know that tensor by K theory doesn't change. Tensor by compact doesn't change the KK theory or K theory. So your cross product actually is just this. And then there is a result, the Tom, Con-Tom, I don't know, isomorphism that says when you do cross product by R, it's the same as doing the same cross product with the trivial actions, which means that it is the same as looking at this algebra tensor C0 of R. And so, and this algebra, this is the cone of an application. It's very easy to compute the K theory. And you just have evaluations, very easy, you put it in negative front. So this was hard, this is very nice. The only problem is that you have tensor by R, but this is a standard thing that Tom isomorphism is working, and then you can forget about it. I mean, you don't forget that. This action looks difficult, but actually you can homotopy it to a trivial action. So you have everything of what you need. Actually, what you prove is that this algebra is KK equivalent to this one tensor C over R. This is a sponge. Okay, so it's geometric in nature, because we really use that we have this space R where we can act. Okay. But that's not the proof I want to advertise. Okay, I want to do two other proofs, which are in the spirit of what Pimsner did. Okay. Maybe I should tell you though, when I said, so Kasparov and Skandalis had this paper on group acting on buildings in '94, where they did the general cross-section using this method Dirac, and okay, you can say that cross-point Z is acting on a building. It's a line, so this R, and so it's very clear what the proof of this is. It's just a special case of much generalized. Okay, but you can just maybe try some other things, and the other one would be the proof 2 using Pimsner algebras. Okay, now I know that there are other ways of presenting these algebras using planar algebras and things like that. I will stay in the which thing I know better. So very naive maybe presentation of these algebras. What do I need? I need a AA bimodule. So E, it's a AA Hilbert bimodule. Okay, that's you have A valued in a product and an action of A as operators on this module. And you can construct the Fogg space. Okay, Fogg space. So it's going to be E plus X sum over 1. And you tensor the E's of A certain number of times. Okay. And on this, this is again a bimodule, and you have natural action of A acting on this and here diagonally, and also you have a natural action of, I mean, you have, whenever you take a vector inside, you can create this vector, and so for inside E, you have this left triations, so acting on some tensor eta 1, eta k. N, which is what you see inside, it's a one tensor. Yeah. And on just A, it's psi times A. Like psi A. Psi A. Okay, so we have creation of operators. And I will call T of E, this is algebra inherited by A and all these creations, the and the X. Okay, I put A, I should not. I mean, I should have said, of course, I want maybe my module to be full so that the inner product generates the whole this algebra A. In that case, I don't have to add this A. Okay, that's an interesting thing with all what Pimsner did is that actually there always a strong link between a particular representation and a general property, a universal cis algebra. And this is here the case. Okay, this algebra is presented as a subalgebra of the operators on the Fock space, but it actually has a universal property. So there is no universal or reduced cis algebra associated to this context. It's just one, this one. So this one strong result. It's the same as, I mean, it's a Kunz algebras or particular case of that. Okay, so, and with that, what about the cross product here? Of course, if you take this particular module, so you take A as A module, and it depends on, and so A is A module, and I act on the left by alpha. Okay, so maybe this is maybe it's the opposite you have to do that. And so if you do that, you will produce an algebra which is not going to be the cross product by Z. It's what we call, in that situation, the Topic algebra is what usually we write this as the cross product by N, but one quotient is going to be my cross product. Actually, we can prove that you have the compact operators of the Fock space in this situation, I think. And if I take the quotient, I will. So this is called the OE algebra in Pimsner, and this will be isomorphic to the cross product. Okay. So this is a general way of looking at my cross product. And what is interesting in this setting is that, so what is difficult is this universal theorem that says that the Toeplitz cis algebra is just obeys to some rules. But once you have this, then the theorem that says that the K theory can be computed is very easy. That's quite strange. So if I recall, I'm saying that I'm vague because this is not. So TE has a universal property definition, which means that it's actually very easy to produce representation of this cis algebra, and this is useful in KKFA when you want to do deformation. You have to be and you have to know when something is a representation of this algebra, and actually it's very easy because of this universal property. So this has a universal property, and so the theorems is that then this algebra is what's called KK equivalent to A. Meaning that, of course, the K theory groups are the same, but more. Actually, we described there are elements in KK groups which are invertibles. And so it allows us to completely describe this in terms of that. Of course, there are also other theorems, maybe I should mention that says that this algebra, for example, is exact when A is exact, or things like that. Okay, so this is difficult, and you have to work to get this one, but this is very easy. So I can try to present how it works. You have to play with representation. So I described one representation. T of E is Fock space, it's natural one. But there are others. And for example, you can you can write this like that. Okay, there is one vector, maybe this one copy of A, and then you have all the others into which I'm going to write like that, adding 0 here, meaning I want transfers of length at least 1. And you can compress the creation operator onto this space. And it actually will be again a representation of the tuplets. So we have, if you take maybe T projection onto this, and if you look at the map that I assigned to psi in E the P L of psi P, and these are going to be maps from E to bounded operators there, and they are going to satisfy the universal property for the tuplets. So you induce a representation, so pi 1 from tuplets onto the operators on the first place. Okay. And using, of course, you see that you have, I mean, this is the 1 minus P is rank 1 projection somehow, because it's projection onto this, which is rank 1 in the correct setting of A module. And so what is obvious that this for all x in T of E, pi, so the pi 1 of x minus what I call pi 0 of x, which is going to be the representation. These are always compact operators on the first space. So this pi 0 is the representation. Now I give a name to this representation. And T of E is a subalgebra of L of Fe, but let's call this pi 0 this inclusion.
What is Fe 0?
This just, you remove the vacuum vectors. So it's tensor of length at least 1. You just, I mean, you just do nothing except that you don't allow to go back to 0 length tensors. I mean, to the A copy in the first step. Okay. And now, with that, you built a natural element in KK theory. I don't know. So this, so pi 0 plus pi 1, if you want, now produce something that's an element alpha in KK 0 of T of E A. What this means is have a T of A module, which is the Fock space. So I have a T of A by module. So it's Fock space. The two copy of it like that. And then you have to have a representation. So the representation of T of A on this is going to be pi 0 plus pi 1, which is diagonal. And you have this T, which is going to be this one. In these two copies of the first space. And so this is really T square is 1, of course, and this self-adjoint. But what is important is that when it's a commutes modulo compact operator with the left action on t. Pi 0 plus pi 1 of x commutator with t is compact. Okay, so this produces an element in KK theory. It's very simple. It's why very simply from the fact that you have this Fock space, and then you can just look at the natural representation, or just a slight different thing, just remove the first 0 length vectors and look at what you have, and still a representation. Okay, and then this is what I need. This is the inverse of the inclusion. So the theorem will be now proposition alpha is the inverse in the KK theory of the natural inclusion of A in theory. And this exactly means that A and T of E are KK realms. Okay. So to prove that this is inverse, you have to do computation, of course. One is very easy, because when you go from A to T of E and back to A, when you compose, so the inclusion of A to T of E with this element, you really see that you have a trivial thing. And because A commutes with everything, so you just are left with what this T is doing, or what is pi 1. So you have just one element left, so it's very easy to see that it is the identity of A, and the tricky part is of course to do the other one. The other thing is that you have this element alpha, you induce now, these are A modules on the right, but using this inclusion, you can make them as T of E modules, and then you have to deform your representation. Okay, and here that it is a very simple deformation. So when I go to the proofs, so I have to look at modules like f of e tensor over A CE, actually 2 times that, and I have to deform. So in here you have 2 representations, pi 0 tensor 1, so the classical representation of T of E into here, where I just act classically in this left part. And you have to compare it with something which is my pi 1 tensor 1. So I act here in a strange way. So, but with plus the identity, so plus identity of T. This is a representation that says, okay, pi 1 actually that is only concerned with tensor of length greater than 1, equal or greater than 1. So you have still a part in here, you have this decomposition. So my bubble, F bubble tensor TE, plus A tensor TE, if you want. If you decompose this space like that, because it's Fock space, the pi 1 is only acting here. And this identity says, okay, I'm acting, A tensor A over T is just TE of A, and you acting as the identity. T acting on T, like the left multiplication. Okay, and so the only thing we have to prove that there is an homotopy between these 2 representations. Okay, and if you do that, you prove that you have the inverse. And now what Pimsner observed, that this homotopy is very simple. It's very simple, at least on the creation of God. So you have pi t, so I can give you a formula. So pi t of a single creation operator is going to be my pi 1, if you want, pi 1 of L of psi, tensor 1. This acts only on a tensor of length bigger than 1, and then I have to do some things in order to compare this, to transform this into this, if you want, And then you just do something like cosinus t pi 0 of L of psi, but just restricted to this A0 tensor TE part plus cosine t. Then let's call this so this just the multiplication now of t, so L of psi. So this is in the same space, but now using this identification. And then I just multiply L of psi on this thing. Because this is very simple. Just for lengths, for creation operators, you don't change what's happening on bigger tensors. And here you just passing from one to the other. It is strange because, of course, this operator is stabilized in space, but not this one, of course. Because when I do that, I create a length 1 vector on the left part of my tensors here. So these and these are not representations, but they can describe operators and prove that actually when the size to this thing is satisfying the correct universal property for the toplets. So you have a representation of the toplets. And when t equals 0 is pi 0, when t equals pi over 2 is the other one, and you're done. Okay? Okay, now why I'm doing this in great detail, because actually this allows you to have an extension of this result. So and since this has been used in a very recent paper, so I'll just state it. So Hartmann and Penis use this. And so there is that, okay, this works for the toplets algebra, but I can look at something which are called mainly semicircular systems. So let's define, okay, maybe somehow you have a subspace or vector space of this A module. And you only consider creation operators coming from vectors here, and even more you are only considering things that are the real part of this creation operator. Over 2 or not very important. Okay, and now you can maybe call S of E, maybe this ER, the cis algebra generated by this with N. This algebra generated by the A's and the Xi outside E. Okay. Actually, if you're not careful, if you're not careful, for example, if you take the whole E, then of course this S is going to be equal to T. S of E is going to be T also. So it's not very interesting. But it is interesting if you indeed look at a smaller set, which is, so this is was observed, not observed, very used very heavily by Schlartenko. And if I just take one easy example, if you take C, so A is C, and E also is C, it's a one-dimensional C bimodule. Okay, and of course this ER is R. Then the toplets is the usual toplets. So this is algebra generated by one isometry. Okay, this is the algebra in the Fock. Maybe I should say the Fock space first. The Fock space of this E is isomorphic to L2 of the integers. The integer gives the length, and T of E is generated by this isometry S, the S on the basis is E of n plus 1. Okay. And then this S of just the one, okay, this algebra of this is going to be, so it's going to be the Sitter algebra generated by the real part of that, and so this is going to be isomorphic to the continued function on 0, 1. Because what you can prove is that the spectrum of the real part is 0, minus 1 to 1. Okay, so it's, this is not commutative, this is commutative, for example, so it's very different. It's algebras. Okay. And now, if I have this semicircular systems, Sitter algebra, the second question, what is the K-theory? And the theorem says that it's not changing, it's the same, it's still A. So S of ER is again KQ equivalent to A. Therefore, to also the Toplitz's theorem. Okay? And what is interesting is that the proof is the same. You basically use the same deformation, and you can do that because actually you have a very simple formula for this deformation. That's the point. Because you have this kind of formula, you can use this to produce a formula for S of psi, because you are taking a Sitter algebra that are generated by actually just this length 1 creation operator with, or annihilation operators with vectors of length 1. And so everything works very nicely. So I said this was true long ago, and then we finished it, we published it with a student and myself, so it's in class. It's in 90 last year. So this part. And it's been used so in the Hartley Penny's paper on planar Sitter algebras, planar Sitter algebras. Okay, but now I want to go to another third proof of the cross-product. So this is the proof because, as I said, there is a choice of the module, so we have the top list is this algebra with quotient the cross product, and I should prove the ideal is the compact answer A, and since you know that is equivalent to A, this is also equivalent to A, or it is equivalent to A, and 6 terminal sequence gives you an answer for this. Okay. But you can say it's quite indirect, okay, because you still need a 6 term exact sequence to really compute what you want. This is here, because this actually was not interesting first. Okay, so let's try to go to a third proof that is actually not using, but was inspired by an earlier paper of Pimsner on group acting on trees. And then he's acting on a tree that is just 9. Okay, so proof number 3. Serre, Jean-Pierre Serre, described group acting on trees in terms of fundamental graph, and this is what I'm going to discuss. So I will use the term of graph, but maybe graph Sitter algebra, but it's not exactly what people call graph Sitter algebra, so it's different. So I have just a graph, which is just a collection of vertices and edges, maybe something like that, whatever. Okay, and vertices, edges. Of course, to each edge I have the beginning and the end. And I will ascribe to each vertex and to each edge the sister algebra. So we have AVs and to differentiate BEs. So for the vertices, for the edges. So these are sister algebras. Any sister algebra. Okay? No need for just matrix or any sister algebra. And then, of course, I want to code what's happening. And of course, if, let's say, for example, the termination of my edge E is the vertex V, then I want to say that the BE embeds into the AV. Okay, so the sister algebra associated to one edge has two embeddings into the sister algebras associated to each vertices. So and your V is V1 equals V2. Okay, you have two embeddings. Okay, and then.
So you assume the graphs are directed since you're talking about source and target?
I need to have a source of the target. Okay. But so yeah, I have E and E bar if you want, but I'm not going to use them much. Or if you want, I'm going to say that this is true. So the sister algebra I put for the edge or its reverse is the same. So I'm safe. And now I want to produce the sister algebra that is generated by this situation. And this, I want to do it as the same way as we do it for groups, when actually you don't associate sister algebra to groups, but to vertices and edges, but groups. And that will be the stabilizers actually of the fundamental graph. So how do you do that? It's a little tricky because you have to choose a tree, a maximal subtree into your graph, because your graph is not a tree, this is not a tree. You have to choose a maximal subgraph. So let's call this Y. Maximal subtree. And then I want to define, let's call this P of my graph gamma as a sister algebra universal for the property. So it's generated by the AVs. So in particular, it contains many copies of BE, because I have different embeddings. And I want to compare these embeddings of the BEs into the AVs. And so what I'm saying that if I have an edge so that T of E is V, and is V1, and the S of E is V2, then I want to have a unitary EU such that maybe something like that, i.e. V1 X U is equals i.e. V2 of X. So the IEs, these are the embeddings of B into AV, and so X is in VE. Okay. So it's generated by the AVs. The BEs don't have many copies, but these copies actually I can change from one copy to the other using this unitary UE. And what's the use of this maximal subtree? This is to prescribe that UE of an edge that is in Y must be 1. So there's one more relation. Let's say that UE is 1 if it belongs to the subtree. Okay, I will show you two very easy graphs so that what I'm saying makes sense. The first is this one. Okay, I have one vertex, one edge. Why not? Okay, so that means that, and I because I want to call something, the algebra associated to the vertex or to the edge is the same. It's going to be A. So that means I have two embeddings of A into A. Okay, so one of the embedding I'm going to think of it as the identity if you want, and the other embeddings I'm going to call it alpha. Okay, and this algebra universal to the property. Okay, if you see this relation, so I have a unitary, just one because I have one edge, and this relation is actually the relation of the cross product. So in that situation, P is the cross product. That's why I need to have this unitaries.
What's y in this case?
Y, there's no y. Y is empty. There's no maximum subtree. So, but now another very simple graph. You have two edges, V1, V2, no, two vertices, sorry, and one edge. And then you see that the y is going to be the graph, the whole graph in this situation, because okay, this is also a tree. So in that case, there is no use because they're all one. And what you have this algebra B associated to that embeds into the AV1, that embeds also into the AV2. And you want to have this set algebra that is generated by AV1, AV2, and that this copy of B that comes from the embedding in AV1 or in AV2 must be the same, because the U's actually are not there, and the U's are the identity, so just the same. So this is the amalgamated free product. Okay, so this is what's happening for groups. Okay, this is the case of what's called HNN extensions. When A is not, when this is not this, it's called an HNN extension, and this is an amalgamated free product case. And of course, in the group case, you can build out of these two things more complicated graphs. Okay, and the theorem of Jean-Pierre said, one of these theorems, it says that actually a group that is acting on tree is the same as this data, and it can be recovered from these two operations. Okay, you can start from this, and then you add edges or loops, something like that, and you can produce any final graph. Okay. The tricky things here is this algebra not zero. Of course, maybe it's zero. This is tricky because I have nothing to really to work with. But the question is this zero? I mean, there are proofs that this is not zero. There are two different proofs that are actually quite hard. I mean, so using very strong statements about representation, because well, you have two. You can represent AV1 and AV2 as you want. You have two representations of these. Why should they be conjugated by a unitary? Actually, this is what we need. But this can be done. But I'm not going to spend too much on this because this is a universal thing, and as well, there is also a reduced version. So that's better. I'm going to the very concrete representation. I'm going to describe what we use. So it's been very fine. Okay, how do you do that? For that, you have to have a conditional expectation. So there is reduced version if there is conditional expectation. Reduced version, so if one has conditional expectation from the AVs back to the VE. Again, in the case where V is a vertex of the edge E. So conditional expectation. In that case, so you can build some AV BE invert space, invert module, and using GNS for this conditional expectation, you produce inner product values in BE and with an action AV on the left. Okay, and then there are going to be so if we choose a vertex V0, I'm going to produce so P gamma A V0 Hilbert module. And we have a P gamma A V0 Hilbert module. Okay. How do you do that? Very simply, you have your graph. Okay. But let's see, maybe this B0 is here. It could be inside. It's not important. And I'm choosing a path that goes to V0. Starts anywhere, but ends in V0. Maybe this way. Okay, and for each element in the path, I can associate it a Hilbert space. So if this is vertex V1 and I take this edge E1, I'm going to take the edge V1 E1 space, and then I transfer it over here. This is going to be a B E1 space which has an embedding into here, so I can transfer over B E over this next the space I can associate it to this next move from this vertex using this edge and up here. So I will have a succession of so A V1 B B E1 transfer over B E1 H A V2 B E2. And the last thing I take A 0. Okay, I can produce this kind of thing. So I have path on the graph, and each path gives me a Hilbert module. AV1, AV0 actually Hilbert module. And if I sum all of this, it's going to be again AV0 that module, but then with an action of this general universal system algebra on the left. This is not trivial, right? You have to check it, and it's clearly an action. Okay. Oh no, I just have to add something. It may happen that I go back. It's not forbidden. For example, in this here, I can go from here to here to here to this several times and then stop here. Okay, I'm not forbidding. It's not forbidden to go back. In that case, it's not exactly the whole space that you're taking. When you go back, you remove the units here. So it's well known that this space contains AV. It contains B, sorry, plus some small things. If you go back, you take this one instead of the whole thing. So there are bubbles here, maybe. Sometimes, when you reverse. So for example, here, what you'd say, so it's just one vertex. It's very easy. And what you can do is going one way or the other way. Okay, but here you are in very special situation where since A is here, the conditional expectation you take is the identity, of course, and then there is no bubble space. Because if you do, I mean, this conditional expectation doesn't produce anything. If I take the identity as a conditional expectation, when I do GNS, I just have the same space. So actually, in that situation, you cannot go back because then what you prove, you use this, but this is 0. And so it will give you the 0 space. So all you can produce when you want to arrive at this edges is either you turn n times like that, or k times in that. Okay, so actually you are very limited. This space is going to be not so big. It's going to be L2 of Z times A. Very small. Here, it's here. Of course, you have two vertex, so you have two space, different ones. And of course, if I want, suppose I want to look at this one, so the paths are just going back and forth. And this is going to produce a reduced part of the reduced free product Hilbert spaces or Hilbert modules you do. Because you have this bubble things that appears all the time because you keep going back, actually. You go there and go back. So this Hilbert module in this situation is the free product Hilbert module you are accustomed to. I mean, part because you remember you have either you stop here or you stop there. And what I'm saying is that you get two representations of the pi gamma on these two different Hilbert modules, and they are not isomorphic. I'm not saying that. Okay? And of course, now to get things a little more complicated, I want to have also Hilbert modules, pi gamma b Hilbert modules. Why should there be Hilbert modules not for the edges? Okay, but then this is trivial. Once you have this, so let's call say curl AV, so the modules here, so curl HV is going to be the sum of all paths of contribution like that kind of thing, all paths that ends in V0. This space, so this is AV0 right module, so you can tensor using the conditional expectation. You can make it a B module. Okay, so this I changed my letters. I'm going to call this K, or maybe not. It's called HE. So this is HB0, and I get HE. Okay, I have even, and then what can be proven is that actually it's just attached to an edge. Okay, so we have an edge E, so you can look at so we have two vertex here and here. Okay, if you take the HV1 and do this operation, or you take the HV2 and do this operation with different conditional expectation, you're going to end up with the same space. Okay, it's not trivial. You have to really see that. Okay, and then, so what is the reduced version of this universal sister algebra that in many cases are just cross product or free products? I mean, okay, that's where it's interesting. So definition. There is so two natural objects. One I call PV of gamma. Is you look at the image of the universal algebra into the sum of all the HVs. So it's image of the universal object in the sum of the HVs. You don't choose about the vertices, because there are many vertices, so many AVs, Hilbert modules. You look at the image there. Or you can look at the image in the sum of all the edge modules. The edge module means that. And you may think it's better to look at these edges. Okay? And so what is interesting is that these are two different objects. Okay, in the case, very simple case of the free product, of course, it's not going to be different. But it might be different in the case of the free product. The cross product is okay, but the free product might give you something different, but only if the conditional expectation are not GNS faithful. Okay, so that's the point, of course, in the free product construction, you always take GNS faithful conditional expectation to do things. Which are very natural to do. I mean, if you do Feynman algebra, but for cis algebra, it might be the best thing to do. Because in cis algebra, we are interested in state or not faithful. It can be very natural. So you get two different things. Can be very different. This can be very small actually. And usually when conditional expectations are morphisms, you get something that might not be bigger than BE, whereas this can be a little bigger. So, and then, but again, same thing if the conditional expectations are GNS faithful. Okay, and then what you can prove first you prove that in KK theory there is no difference between PV, the reduced one, and the full one. So PV of gamma is KK equivalent to P gamma. Okay. So PV must exist, so there must be some conditional expectation. But for any conditional expectation you're taking, this is always equivalent to this, even if it's very degenerative conditional expectation. Okay, and then the theorem, so this is answer 1, and then theorem 2 says we can compute perfectly the curvature of this one in terms of the AVs and the BEs. Okay, that PV of gamma, KK theory of PV of gamma is computed of the AVs and the BEs by a formula that were given by Pimsner in the beginning, okay, which is a very, there is a 6-term exact sequence, because, for example, let's write this just for K theory. You can just look at the K theory of all the BEs. Of course, the BEs embeds into the vertex sister algebras. So you look at all these embeddings. The AVs actually are subalgebras of this sister algebra. So the reduced version of the full version is not important, it's the same. And then you have this boundary map. So this, if this is 0, of course, then you go to K1, the sum of the V's over the K1 of the E's. And then okay, it's what is it? It's very simple. And the point, so this is true, this was true for groups, but now this is true for this general construction. We just have algebras, no groups. And the map here is very natural. It's actually a map that is as nice as the one I described you for the Kunz, in the Kunz case. To have a very natural element that goes from this into this, or have a very natural KK1 element from the P gammas into a module of a PE. Okay? And how do I construct this element? I take this, of course, module, which has a representation of P gamma on the left and is the P module. And since I'm considering a KK1 element, I need to have a projection here that is special. Okay, and indeed I have a very special projection that arises from an isometry, partial isometry between this space and the AVs. Of course, I'm a little late now, I realize. So, but it's very natural. It's not, you don't look too much to find this KK1 element there. The boundary map is completely obvious in some sense. It comes from geometry of all these similar spaces where you can compare them actually in many ways. And so what's important is, I should add, just this, there is an isometry between this space and, okay, these are not the same, so I take E, but I deduce it to AV, so that it makes sense. Okay, this is module of a P, V is a subalgebra of the AV, so I have here a partial isometry. In the free product case, it's an isometry, but otherwise, just maybe a partial isometry. And what's interesting is that when you look at the range projection, so UV star, the range projection is living here, and actually it's a projection here. So it's a PE tensor 1. God, it's a projection that is actually just in this part, and not in when I have to tensor with A. Okay, and this is the projection you use to produce your KK1 element. Okay, and then you have to check that it works. That this is the exact sequence. This is hard, of course. I mean, but the building blocks come from considering all these tensors. There is no geometry actually, the classical geometry involved. I have no, but I can still prove. I mean, this in a particular case, you have the cross product. For example, or you have any groups that are H&N of free products and negative free products. Okay, I'll stop here because it will be too long. Thank you.
Any questions or comments for the speaker?